So in this activity, we're going to try to extend our notion of position time graphs. And what we're going to do is give you some scenarios. And the first one's going to be a person walks across the classroom at constant speed. They quickly change direction, and they walk back to where they started at constant speed. So it's still mostly constant velocity, but we'll have some rapid changes in it. And that's going to make the graph slightly more complicated. So what we're going to have you do is you guys will make an initial prediction of what you think the position time graph would look like for each of our motions. We're then going to have you guys get in groups and kind of compare with each other what you got and argue it out. And if you feel like you need to change your position time graph after talking with your group, you have some space to do that. We're then going to look at the motion, and there's a computer program called Tracker which does something called video analysis. And that will let us take a look at a moving object and see what the graph really looks like. So if you need to change it here, you can do that. And then there'll be a place for you to explain why your thinking evolved. So let's take a look at this first motion. All right, here I go. Graph number 1. So this program is called Tracker, and it lets us take a video, and every picture that's a frame of that video has the object in a certain location. And as the video moves through its frames, that's actually measuring the motion of the objects in it. And all we have to do is tag where the objects are in each frame, and Tracker can make a graph of their motion. So let's use my head as an object, and we'll see what the graph looks like. We'll talk about how to use Tracker at a later time. But right now, let's just get the graph. So I guess we'll use my nose. And what I'm doing is basically tagging as if it's a Facebook picture where I am in each frame. So far it's looking pretty linear, which means I'm moving at a constant velocity. But as you know, that changes. So now I'm moving backwards, and look what's happening to the graph. All right, so that's what the graph of motion looks like for someone who moves at constant speed, first in one direction, then very quickly stops and goes back the other way at the same constant speed. So hopefully that's what you predicted, and if not, you're welcome to change it. Obviously, something else is going on here. You see this curve here. We're going to ignore that at this part of the class, but this is where the velocity is changing. There's something called an acceleration. And that'll be what our next topic we're studying. But right now we have a segment moving forward at constant velocity and a segment moving back at constant velocity. Alright, so hopefully you have something like this after seeing the data. You may have a slight curve at the beginning and the end. You may have a slight curve at the top. And that's because I can't change my motion instantly. I actually have to slow down and change direction and then speed up in the other direction. But this is a reasonable approximation since I was going pretty slow and the change was quick. Key thing I hope you got out of this is that motion in one direction, we can call it a positive velocity, has a positive slope. And motion in another direction, we can call it a negative velocity, has a negative slope. So we can tell direction based on the sign of the slope. Let's look at our next motion. Alright, so in this one, the person's going to start out walking in the positive direction, and then they're going to stop and remain there for a while. So go ahead and make a prediction of what that looks like, and then we'll look at the motion. Alright, here comes graph number 2. Alright, so here's what that looks like. So again, just tagging right on my nose. It starts out pretty similar, as we expect, because it was constant velocity in the positive direction. So we're getting a pretty linear graph. Alright, so now I'm not moving anymore. Look what's happening to the graph. Now we've said slope is the velocity, at least on a position time graph. So what does it mean to have no velocity? Well, you must have a slope of 0. And that's what we're seeing here. So if someone stops, a position time graph reflects this by showing increasing times, but no change in position. And that's what a horizontal line looks like. Alright, and here's our final trying to predict the graph question. In this case, a person's going to walk constantly in the positive direction, stop, then walk at a constant speed in the negative direction, and then stop. So try to predict what a graph would look like for that. Here's the motion. Alright, here's graph number 3. Okay, here I go. So moving at a relatively constant speed, except at the beginning, of course, when I had to speed up. Now it looks like I'm changing. I'm barely moving the mouse at all. So this is that coming to rest period. See how the graphs change just like before. So at some point I'm going to start moving backwards, and how do you think that's going to look? I wonder what I'm looking at. Probably just trying not to crash into anything. But if you look at the graph, you can see it's representing negative velocity, or moving in the negative direction. So this is interesting. I'm crossing my initial position. And look what that means. Now I'm actually below the x-axis with negative positions. That just means I've gone beyond the starting line. Alright, and now it looks like I'm stopping again. And there's another place of 0 slope and 0 velocity. Okay, so now we're going to go in the opposite direction. We're going to give you guys several graphs, and you're going to be responsible for writing a sentence describing what the object in each case is doing. You're then going to confer in your groups and make sure you all agree, because one person from each group, and you guys get to pick who in each group, is going to come up and demonstrate each of these motions, act it out in class. So we'll assign which group gets which graph randomly. So make sure you're familiar with all of them. The hope is by the time you're done with this, you're familiar with what a graph is showing. What do positive x values mean? What do negative ones mean? What does a positive slope position time graph mean? What does a negative slope mean? What does a zero slope? So if you've got all these things out of this exercise, that's great. That was what the intent was.